So when discussing things like correlation and causation, you need a language or a frame to discuss these questions. And there are at least three frames. First of all, you have the frame that focuses on regression analysis, and that's standard economics. One first frame is in economics, and they focus on regression analysis, and that's associated with people like, for example, Heckman. And what you do is basically look at the variables you're interested in, y. Let's say that is the blood pressure of a person or the salary of a person, and you say this is, you do a regression and you say it's a constant that's going to affect the blood pressure. Then you have a variable, the intervention x, and then you try to find whether this is a significant variable or not, and then you have some other variables, beta 2 z, that also affects blood pressure or salary. And you're interested in the causal effect, basically trying to measure this, and you condition on a lot of other variables, meaning you control for or adjust for the influence of other variables before you say that this one has a causal effect. And that's what you do in economics usually. Now the second approach to causal inference is, and this is more used in statistics and sometimes in medicine, in statistics, and they use something called the potential outcome model, and this is also used in economics, but they tend to use it a little bit more in statistics. Potential outcome model, and it's associated with Rubin and Rosenbaum. And the way they do it is they first define causation in terms of what a person would have had if he had not received the treatment. So they define two variables. Y1 is, for example, the salary a person would have if he received treatment, but the same person, so this is Y, person Y, the same person would have a salary if he had not received the treatment, Y0. Now the causal effect is the difference between the two. The salary you would have with treatment and the salary you would have had without treatment if you had not received treatment. So let's say this is the causal effect, Y1 minus Y0. The problem being, of course, you can't identify this because you don't have both the information at the same time. You can't both give the treatment and not give the treatment to the person. So you're left with a missing variable problem. You can have this one or you can have this one, but not both. And one way of solving this is by looking at populations or samples, because you can give treatment to some people and not give it to other people, and then look at average difference. So you can look at expected value Y1 among those who received the treatment and subtract the expected value, or the average basically, for the people who did not receive the treatment. And then you can try to say this is the causal effect. Take the average among those who received the treatment and subtract the average among those who did not receive the treatment. Of course, the problem being that the people who received the treatment could be special. They could be a different group. So that's why they tend to focus on randomized experiments, because then they shouldn't be different. They could be. So but this is one way of discussing the problem and one way of framing it. The third way I wanted to show you is used in computer science, and it's an approach based on graphs, and it's associated with someone called Judea Pearl. Now, this may look simple, but it's actually gives quite a lot of insight. So let's say you want to look at the association between, or the correlation and the causation between drinking and blood pressure. So let's say drinking could be caused by lots of different things. You just draw a graph of all the things that could cause drinking. So let's say drinking is here, D, which could be caused by A or B or C. And then drinking will affect your blood pressure, Y. But the blood pressure, this is drinking here. The intervention you're interested in, this could be blood pressure, or it could be wage or salary, whatever it is, the outcome. So blood pressure in this case. Now, there could be other things affecting blood pressure except for drinking, of course. So let's say you have two other things here. F and G. And let's also say that there's a common variable between A and F. You don't know exactly what it is, but there's something that connects A and F, which could be a common thing behind both A and F. And same thing between A and B. There could be a common factor behind both of those. Okay, so this is the way they try to first make sense of the problem of causal, how to identify a causal effect by drawing a causal graph like this. And then you try to see, okay, I want to isolate the effect of drinking on blood pressure. But I also see from this graph that a lot of other things will affect blood pressure. You could have something that goes to A, which affects F, which affects blood pressure. But A will also affect drinking and blood pressure. So you have many causal paths, basically, many paths going to Y, and you need to block those paths you're not interested in this framework. And you don't have to draw graphs always. They do have a formal language in addition to the graphs here, but this is the basic idea, and it gives a lot of insights. So these are 3 ways of framing the problem, and they have some advantages and disadvantages, but basically it should give the same result. But they focus on different things. And you should know that there are at least 3 ways of doing it.